The third objective in 2.5 is that the student will be able to apply base E exponential functions, including growth and decay applications. So base E, growth and decay applications. Functions of the form y equals ce to the kt, where c and k are constants, and the independent variable t represents time, are often used to model population growth and radioactive decay. Those are just two applications. One is a growth application, the other one is a decay application. Note that if t equals 0, then y equals c, right? Because if you have y equals ce to the kt, and you let t be 0, y equals ce to the k times 0, y equals ce to the 0, but what is anything to the 0 power? 1. C times 1, which is 1. C times 1, which is C. So if t equals 0, then y equals c. So the constant c represents the initial population or initial amount, right? Time t is 0. We're at time 0, right at the beginning. And when we are there, then the population has the value of c. So whatever the coefficient of e to the kt is, that's what you have at the very beginning. Constant k is called the relative growth rate. If the relative growth rate is k equals 0.02, then at any time t the population is growing at a rate of 0.02y persons, 2% of the population per year. So there's a growth rate, there's an initial amount that we can see just from the equation that we're given. We say that, okay, now here's a formula, a very important way of putting words together. Population is growing continuously at relative growth rate k, to mean that the population y is given by the model y equals ce to the kt. So that's the way to say in words y equals ce to the kt. It's not the only way to say it. Sometimes they call that the law of uninhibited growth, but that's a way to say it. Population is growing continuously at relative growth rate k. The atmospheric pressure P decreases with increasing height. Okay, so imagine yourself, you're in a hot air balloon. Atmospheric pressure P decreases with increasing height. The pressure is related to the number of kilometers h above the sea level by the formula. P of h, okay, that's right, atmospheric pressure P, that's the same P when we write P of h. P of h equals 760 times e to the negative 0.145h. So that's how height above sea level in number of kilometers is related to pressure P. One problem that we have to be able to do is to find the pressure at sea level, h equals 0. The other problem we want to be able to do is to find the pressure at a height of 7 kilometers. So at sea level, height is 0 at sea level, isn't it? H equals 0. So we're going to substitute 0 for H, and then we get e to the 0, which is 1. E to the 0, which is 1. And 760 times 1 is equal to 760. So that's the pressure, 760. Other problem, find the pressure at a height of 7. Well, we're just going to put 7 in there for H and go to the calculator with that. We have to make sure that we do the exponential before we do the multiplication by 760. And actually, the very first thing we have to make sure we're doing is we're doing this multiplication in the exponent before we're doing the exponentiation, before we're doing the multiplication. Then calculator will give 275.43 for the pressure. Here's exponential decay. Depreciation of a machine, how it becomes less and less, has less and less value as it's used over the years. A machine is initially worth V naught dollars, V sub 0. And so, in other words, that's the value at time 0. But loses 10% of its value each year. Its value after t years is given by the formula V of t equals V naught times the teeth power of 0.9. That's funny, teeth power. Find the value after 8 years of a machine whose initial value is $30,000. So after 8 years, what is that machine worth? Well, t is 8. Do the exponential, 0.9, raise that number to the 8th power, multiply the result by 30,000, the initial value, and you get the value 8 years after it has been used, which is $12,914. We might have had a different problem. Not in this section, but in the next. With the methods of the next section, we'll be able to solve for t. You know, what if they said, how long would it take for this machine, how long would it take for the machine's value to depreciate to $12,914? Well, we would have had to solve for t in that equation, and that requires methods that we don't know yet that we're going to learn in the next section.